cloud. Okay, so today we're going to do more internal forces. I'm going to start with this problem from the practice. I'm going to doctor it a little bit. Am I going to doctor it? Yes, I'm going to doctor it so that it'll have something else. That so this is a problem, question 19 to 21 from practice 10, internal forces. And so the way they drew it, I'm going to change it a little bit. So they drew it like, well, I'll draw theirs and then I'll just kind of change it. Okay, so then we got 2 meters right here, 2 meters, and then they got 3 meters here, and then they got 2 meters here. So I went a little overboard here. Come on, you can do it. Okay, now the way that they did it, so here's a 30 kilonewton right here. Actually, let's solve theirs and then I'll alter it. So this is theirs. Yeah, it's got a roller here and it's got a pin here. And then right here, it's got a force coming down, which they say, for me, it's 82 kilonewtons. Obviously for you, it'll be something else. And this is 30 kilonewtons per meter. Okay. They give you some points here too, A, B, C, D. All right, now I don't really remember what the question is. Oh, free body diagram of the complete beam. Some other free body diagrams. And then they want the shear and bending moment diagrams. Okay, so, all right, so this is what's given. And what I'm gonna ask you to do is I'm gonna say, give me the shear and moment diagram. Don't ask me why shear is V, I have no idea. Why is it V? And what they want to know is they always want to know the max shear and the max moment. And that makes sense because that's the thing we need to design this beam for. If we knew that this is how it was going to be loaded, then we want to know, what it's going to, what it needs to hold. So to me, that just makes a lot of sense. Okay, so, all right, so hopefully y'all can see all that. So what we're gonna do here is we're gonna go ahead and solve this thing. We're gonna do the reactions. I'll do the reactions in red. So here's one, we're just gonna call that B. And here's one that's gonna be D and the Y. D and the X is gonna be 0. Without doing any work, we should be able to see that D and the X is 0, right? Because the sum of the forces in the X is 0. So therefore, D and the X is 0. So if anybody wants me to see me write that out, I will do it, no problem. But I think hopefully we're at a point where we can see that. All right, so then what we want to do is, well, we can sum forces into Y, but that's not going to help me solve for B and dy because I'm not really going to be able to, let's just go ahead and do it. Okay, sum forces into Y. Hopefully you can see that there's 2 unknowns in that direction. So B plus D in the Y. And then I'm going to subtract that 82 kilonewtons. And then I'm going to subtract that 30 kilonewtons per meter. But that's a kilonewtons per meter, so we need to multiply it times the meters it's acting over, which is 2 meters. Okay. So, so what's that? I mean, so B and dy equals, if I bring that over to the other side, what's that, 142, I think, kilonewtons. Okay, so we can't solve that equation yet, but there it is. Okay, so then we need to do the sum of the moments, and we can pick either location D or B. I always like to choose the location that is kind of on the end if I can, just because then I'm measuring all my distances towards the end. You could have chosen B if you wanted to, but let's do in the Z direction on location D equals 0. So let's see, we've got an 82 kilonewtons. By the way, please stop me if any of this doesn't make any sense to you. At this point, we've done this a lot. So 82 kilonewtons is causing things to go, which way is that? That's counterclockwise. Okay, and its moment arm is 2 meters. Okay, and then we've got B plus, well, maybe not plus, it might be minus. There we go, B. And its moment arm is 5 meters. Okay, and it looks like it's going to cause things to go clockwise. So that's a negative. And then we got this 30 kilonewtons per meter, which is acting, it looks like it's going to have to act at its centroid, so right in the middle there. And so ultimately we can replace that 30 kilonewtons per meter times, if we multiply times 2 meters, it's like it's a 60 kilonewton force acting right there. So we'll go ahead and say 60 kilonewtons, and that's causing things to rotate this way. So that's that's counterclockwise. That's a plus 60 kilonewtons times what's that? 6 meters is its moment arm equals 0. Okay, so we can solve that. Okay, so let's see here. 360 plus 164 divided by 5. Well, why would they do that to us? 104.8. 104.8 kilonewtons. Okay, and then from up here, then I can say then if that's the case, then that dy equals, if I plug that 104 in, I get by, not, dadgummit, dy equals 142 minus 104.8, 37.2 kilonewtons. Okay, so usually at this point, I try to think whether or not this makes a whole heck of a lot of sense. And it kind of does. Like, you know, I usually can't tell like what the number should be, but usually I can kind of tell which one should be larger. Notice that B basically is going to take all of this 60, right? Because all of the 60 is to the left of B. So B is probably supporting almost all of that 60. And it's probably getting maybe not half of this 82, but almost half, because this 82 is somewhere between B and D. So it makes sense to me that B would be larger than dy. Okay, so I just like to do that every now and then to kind of, you know, keep me sane and go, okay, yeah, this is kind of making some sense. Okay, so let's see. All right, so now we got these two forces. And so what it's going to want here, and we're going to work on this one for a little bit today. First, I'm going to erase all of these because these no longer help. This number right here no longer helps. That 60 no longer helps, because we don't actually have 60. We actually have 30 kilonewtons per meter. But this B and this dy, I'm going to go ahead and replace them with their actual forces because I think that that's going to be helpful. So the B is going to be 104. Come on, do it. 104.8 kilonewtons. And the dy is 37.2 kilonewtons. Okay, and actually I did forget to erase this one. Okay, because that's just added noise at this point. Come on, you can do it. No, never mind. Okay, so this is 2 meters. All right, so what we do at this point, when you're drawing these things, I highly recommend a ruler, highly recommend graph paper. It just helps a lot. Okay, so what I'm going to do as best I can is I'm going to draw some vertical lines at the points where things change. Okay, and they change basically wherever there's a force. Okay, and this is how we do this. And then, so we'll start with the V diagram. Okay, a V or shear diagram. So this is V. And what we're going to do basically is we're going to look at this diagram, and there's going to be shear wherever there's a force in shear. Okay, so it's not worried about axial forces. So it's not worried about forces that are going along the beam. It's only worried about forces that are going perpendicular to the beam. Okay, because that's what shear is. It's going perpendicular. Okay, so let me erase those triangles as well. I mean, those arrows as well, but we're only worried in this case about things that are going up or down. And so we're going to do what it tells us to do. Okay, so this first thing is, the first thing we come through if we start at A and we go to the right is, well, we've got this 30 kilonewtons per meter down. So we're going to go down at 30 kilonewtons per meter. So every meter to the right, we go down 30 kilonewtons. So the net total of all of that is we're going to be down 60 kilonewtons per meter. Not per meter, sorry. We went down a total of 60 kilonewtons. Okay, So then we get there and we went down because this thing was downwards. Okay. Now it is pretty typical to like shade this. Not really necessary, but whatever. Okay. So now we get to this point and we've got an upward force of 104.8. So I'm going to go up 104.8. So we're going to go like this. And that's going to get me to what? 44.8. 44.8 kilonewtons. Okay. And so now at this point, nothing happens for a while. Okay. So we're going to stay at that value until something changes. Okay. And then we get that 82 kilonewtons down. So I'm going to go down by 82 kilonewtons. So I'm going to start at 44.8 and I'm subtract 82. And so I'm going to go down to negative 37.2. Okay, that result should not have been surprising. Well, it's not surprising to me, and at some point it won't be surprising to you. So this, well, let's get some negative numbers on here. Negative 37.2 kilonewtons. Okay. And then, well, nothing changes from C to D. So we're just going to go flat until we get here, at which point we're going to go back up this 37.2 to get back to 0. Okay, if you've done your reactions correct, your shear at the ends should be 0. Okay, so yeah, usually we shade this. I don't know why it usually gets shaded. I don't really think it's that important, but it's not a bad habit to get into. So right here, when it says, so this is the V diagram, the shear diagram, and then what is the shear max? Well, we just look for the biggest value we have here because it always asks in absolute value terms. They don't care if it's shearing this way or this way. It's just like how much shear does the beam need to be able to resist? And so it looks like it needs to be able to. So it's 60. Okay, so if it can't resist 60 kilonewtons of shear, then what's going to happen is this beam. It looks like, well, I mean, I'm not sure which way my hands are relative to your screen, but basically the left-hand side of this thing is going to go down and the right-hand side is going to go up, probably somewhere between B and C. Oh, no, sorry. Somewhere between B, just barely to the left of B. The left-hand side would go down and the right-hand side would go up. So basically what would happen is the way this thing would fail is a crack would develop right here. And that whole thing would just kind of like shear off. Okay, now let's hope that we designed it so that wouldn't happen. Okay, so now that's the shear diagram. And the moment diagram is basically what we're going to do is we're going to integrate this thing, and we're going to integrate it graphically. And so what we're going to do for that, let's see, so we need a moment line. Okay, and this requires a little bit of artistry. Okay, moment. Let's see. And the moments don't necessarily have to go to 0 at the end. They will in this case because there's no moments at the end. But what I'm gonna doctor this problem, and we're gonna do it again, and I'm gonna do it where the moments don't go to 0 to show you what that might look like. That's actually a pretty common result. So what we're gonna do here is we're gonna start adding, and the way I think of it is we're gonna add little boxes. And so we're gonna start at 0, and we're just looking at what the shear diagram tells us to do, basically. Okay, the only other thing that we were gonna include in this is if there's any moments from up here. Okay, but there's no applied moments in the top, so we're not gonna do any of those. Okay, so what we're gonna do is, let's see here. So I'm gonna start here. And what I'm gonna do is add what I see in the box above me. So basically, I'm gonna add this little bit right here. Okay, and then I'm gonna be like, okay, so that's a negative bit. So I'm gonna add that. And then I'm gonna add this little bit. But notice that that little bit is more than I added a second ago. So the change from one position to the next is gonna be greater. Okay, and then the next bit, I'm gonna add this little bit. Okay, and that bit, well, see, I've gone a little crazy here. You know, let's say the first little bit I add was like this. Come on, you can do it. It's like this. And then the second little bit is like this. And then third little bit is even more. Okay, so it's doing like this. And hopefully what you can see is as I add these things, each one that I add is a little bit bigger. So the net effect of that is we're going to have a curved line. Okay, now obviously, like, I can't really draw that because I'm going a little crazy here with the curve. But what I can do is I can draw it more like this. Okay. And the nice thing is, and we're going to do this in a second, we're actually going to get the equation for that line. But I know where this thing's going to end up. I know what this value is right here. Because what I'm going to do is it is the starting point plus the area up here of this triangle. Okay, so the area of that triangle is 2 meters times, well, I don't need that 2 meters right there, but 2 meters from right here times 60 divided by 2, the area of a triangle, 1/2 base times height. Okay, so this is going to be 60 kilonewton meters, okay, or negative 60 kilonewton meters. Okay, does that make sense? I hope. Okay, I see no faces except for Hannah's and Stephanie's cat. So so just please holler out, let me know. Okay, this next section here, okay, I'm going to start at my starting point, and I know where I'm going to end up is going to be, I'm going to add this area of this rectangle. Okay, so it's 44.8 times 3. Let's see. There, 44.8 times 3 is 134.4. And I'm going to start at 60. I'm going to add negative 60. I'm going to add 134.4. And I'm going to end up 74.4. Okay, so I'm going to end up somewhere up here at, maybe that's a little high, I don't know, 74.4 kilonewtons times meters. Okay, now the shape of that line is something we need to think about. And we see that the amount that I'm adding in the first bit and the amount I add in the second bit and the third bit and the fourth bit, I'm always adding the same amount for each bit of x I go to the right. So this is going to be a straight line. Like that. Okay. And then for this last bit, okay, notice it's I'm going to be subtracting the same amount for each of these lines. Okay, so the expectation is it's going to be a straight line. It's going to have a negative slope because we're going downwards. And then I need to figure out how much that is. So, well, we need to figure out the area of this rectangle. So that's 37.2 times 2. So it's 74.4 negative. So I'm going to go down 74.4. And we'll go down like this. Okay, and I'm going to end up back at 0. So this one has, so again, normally we would shade those values. One thing that I will note, I think we talked about this last time, was that this area right here is smiling. Okay, if you have a positive moment, then you've got a smiley. Okay, this area over here is frowning. Okay, meaning if we go up to this original beam, let me do this kind of in green, that basically, like, let's just imagine, I'm going to draw a little line up here like this. Okay, everything to the left of that line is going to it's going to bend like this. Okay, it's got a frowny face. Okay, and maybe I could be a little bit more pronounced there, because everything to the right of that is going to smile. Okay, so in other words, this bit is concave down and this bit is concave up. Okay, if I were to draw how the beam is bending. Now, of course, I don't actually know how much. I'm just this is artist's interpretation, right? Like as you get into further classes, they'll talk about how much deflection you can expect, but that's the idea. So it's going to be smiling to the right, frowning to the left. All right. So now, cool part. We're going to find. So let's see here. Let's go ahead and do this. moment max. Okay, so the max moment that we need to deal with, it looks like it's 74.4 kilonewtons times meters. Okay, meaning if we were to expect this thing to fail in bending, we would expect it to fail right here, right at C. Okay, that's where we would expect it to just kind of like snap, right? And it would either snap because this side right here, like the top side, would either just buckle or the bottom side would tear. Okay, so I guess it depends on what it's made out of. You know, if this thing were a rope and it was just made out of like, you know, nylon, well then I guess we would expect it to buckle, you know, because ropes do pretty well in tension, but not so well in compression. Anyway, so what we want to do now, the last thing we want to do, and they didn't ask you to do this, but we're going to do it anyway. We're going to go ahead and find the equations of these lines. Okay, and so the way we're going to do this is I'm going to erase all this shading in here. I didn't want to do that. Okay, that's all right. I'll just freehand that. Okay, so what we're going to do is, so this line starts at 0. So from 0 to 2 meters. Okay, we're going to start at 0. I guess the moment. The moment, oh, come on. Moment equals 0. Okay, because we're going to start at 0. And then we're going to subtract because all of this is negative. Right? We're going to subtract the area of that triangle. And the area of that triangle is, well, it depends on where we are, right? So the base of that triangle is going to be x. Okay, so it's going to be 1/2 of the base. And now we need to get this height of this triangle right here. Right, and so how do we get the height of that triangle? Okay, well, we need kind of like a rise of a run here sort of thing in order to be able to get that, that height. Or what we can do is we can say, okay, well, I know it's going to 60 kilonewtons. Okay, from 0, so this is the rise. Or I guess it's going negative 60. Okay, and what was the run? Well, the run, so this is the slope of that line. So the run, it went from x to 0. That's not very helpful. No, to get to 60, we went to 2 meters. Okay, so the slope of this line is negative 30 kilonewtons per meter. Well, that's interesting. We already knew that. Okay, we already knew that from up there. Hold on a second, I need a fan. Okay, so the equation of the shear line, shear is a function of x equals, 0 minus the slope, 30 kilonewtons per meter times x. Okay, the moment equation, moment is a function of x. This is probably an easier way to do this. The moment is a function of x equals, basically we're just going to integrate that line. Let's just go ahead and integrate that line. And you'll see this negative 1/2 x is going to come out. Okay, so we're going to integrate the shear line. So the 0 goes away. Negative 30 kilonewtons per meter, okay, remains. Okay, and this is going to become, that x is going to become x squared on 2. Okay, and then what's the thing when we integrate? What's the last thing we always need to do?
Plus C.
Plus C. But in this case, it's going to be plus just some moment. Okay, I'm going to call that a moment 1. Okay, or in this case, that's going to be moment A. Okay, so it's basically going to be whatever moment we need to make this thing work. Okay, so in this case, what I'm going to do is I'm going to plug in x equals 0. So that causes this bit to go away. Because at x equals 0, the moment at A is 0. So if I plug in x equals 0, sorry, this moment then needs to equal 0. And to make that happen, you know, this moment, this constant moment here needs to be 0. Okay. So in other words, the equation for this line right here is, so this will go away, is m as a function, m as a function of x equals negative 15 kilonewtons per meter times x squared. Okay, and notice this is a parabola, and that's the shape we have here is a parabola. Okay, so then what we do is if we wanted any other lines in this thing, okay, we could do it pretty simply. Okay, so like for example, let's suppose we're going, let's suppose we're, no, come on. Let's suppose we want the, from 2 meters to x to 5 meters, 5 meters. Okay, so that's this section here. Okay, if we wanted the equation of the shear, V of x, well, that's 44.8 kilonewtons. Okay, so if we want the moment of x, okay, we just got to integrate that. So that's 44.8 kilonewtons. Okay, integrate that. So it's going to be multiplied times x. Okay, plus some moment. That's your plus c. Okay, and I'll just call it m2. Okay, and so we have to say, well, when x is 2 meters, 44.8 kilonewtons times 2 meters. Okay, this moment needs to kick out 60 kilonewtons per meter, 60 kilonewtons times meters, plus m2. Okay, so if we do all of that, let's see, let's get m2, and we'll say 44.8 times 2, 89.6, 29.6. That's interesting. That is not what I was expecting. Have I done something wrong here? Oh, this is a negative 60, isn't it? It's a negative 60. Okay, right. 44.8 times 2 plus 60. I wasn't expecting 149.6 either. Huh. Oh, yeah, okay, that's fine. All right. Okay, yeah. So we're going to get M2 equals negative 149.6 kilonewtons times meters. So that means basically I could go back to this equation right here, and I could erase this, and I'll get negative 149.6 kilonewtons times meters. Okay, now what is that weird number right there? Anybody know? What is 149.6 physically? It doesn't really have a physical meaning on this problem, but anybody? Okay, what it is if I were to continue this line back to the y-axis. So if I were just to, oh, of course it erases. So basically if I continued this line back this way until it hit the y-axis, that would be the y-intercept. Okay. So anyway, so that's the slope of this line. That's the equation of this line. Okay. And then we could do the same thing for the last bit. And we'll just do this right now, and then hopefully we can get one where it becomes a little bit more interesting. But you know, as to why we might do this. So we'll go 5 meters to 7 meters. Okay, the V of x equals, looks like the whole time it's negative 37.2 kilonewtons. And then we could say, okay, what's the moment of x? Equals, we have to integrate that. So it's negative 37.2 kilonewtons times x plus m3. And then we would just solve for m3 by plugging in, you know, a point that we know. Easiest point here would be that the moment is 0 when x is 7 meters. Okay, and then plus m3. So that means m3 would end up being, what, 7 times, well, 7 times 37.2 is 260.4. 260.4. 260.4 kilonewtons times meters. Okay, sorry, it's getting a little small in there. Okay, questions? Okay, that's how we would get these equations. Okay, if you wanted them, and really the reason that you might want them is because if somebody said, well, what is the shear at a specific location? Then you have this equation. Like now for most of this, for areas in here and here, the shear is pretty trivial. Like you can see what it is, but you also might, want it in here, or you might want to know what the internal moment is at a particular spot between 0 and 2. So that's where, these equations might be very helpful. Okay, any questions before I do one that I think is a little bit more interesting? Okay, I'm gonna do one a little bit more interesting. Let's see here, clear all drawings. Okay, so what you're gonna see here is one really great thing about these problems from a teaching standpoint is that they're very easy to make up. Okay, so I'm gonna draw a random beam. I'm gonna make it up. Okay, and this time, it's going to go into a wall like that. And I'm going to give it let's be weird about this. Let's make it go from there to there. Okay, with a distributed load. And then let's go right here and say on top of that distributed load, we've got another load. And let's get a load right here. I mean, there's really not a whole lot of very interesting things you can do with them, unfortunately, but that's okay. Let's go ahead and have 2 distributed loads. Let's have another distributed load over here. Okay, and we're going to say that this thing is, I don't know, 8 feet long. So this will be 2 feet. 2 feet. This will be, looks like that's about 3 feet. This is about 3 feet. And this right here will be 1.5 feet. And let's see, let's make some stuff up. All right, let's have this be 100 kips. Let's have this be, I don't know, 20 kips per foot. Let's have this one be 30 kips per foot, 30 kips per foot. Let's have this one be, I don't know, 50 kips. All right, so a lot of junk. All right, so the nice thing is I just made this up. The nice thing from my standpoint is I just made this up. The bad thing from your standpoint is, you have to hope that your professor is careful not to make up things that become ridiculous. So I just made this one up. So it could become ridiculous. On a test, I'll be more careful. Certainly on the exam, I'll be way more careful. So what we need here is, well, we need to figure out what's going on here. So this particular beam right here, because it's not because it's like attached to the wall, we could have a force going upwards, which I imagine we will have. So, we could call that F, I don't know, Fy if we want to. We could have an Fx. Fx is trivial in this case because there's no lateral forces. So when it's some forces in the x, it's just going to add up to 0. So we're going to go ahead and erase that. And then we're going to have a moment because this is not a pin connection. This is it's like part of the wall. So the moment, typically I like to draw them, moment in the z. Okay, I like to draw them positive because that just makes my life easier. Okay, so over here on the side, we're going to go ahead and we're going to do our reactions. Okay, by the way, at this point, I'm hopeful that, you guys are getting reactions. By the way, Hannah, I keep worrying that your cat is going to attack Stephanie's cat, because y'all are like right next to each other, and I just see Stephanie's cat, and every now and then I see your cat. Hopefully Austin and Parker don't have cats running around because this could get really sloppy.
I think we have math class together too, so we have our cats up on screen.
Oh, right on, right on.
Their sustainability.
Yeah. And Rocky, fortunately, has not decided to grace this particular problem-solving session with his presence. So anyway, so let's do some reactions. So to do this, I like to just kind of like pencil in what these forces are. So there's 20 kilonewtons feet, kips per foot times 2 feet. So that's about 40 kips. Well, that's exactly 40. And that's measuring, that's going to be at that centroid of that force going down. So it's a rectangle. So it's going to be right at 7 feet from the end. And this 30 kips per foot times 3 feet, that's a 90, which is going to go right here on top of that 50. All right. So now to do the reactions, force into y is luckily pretty easy. Because basically so the sum of the forces into y, well, this is going to come out pretty simple, right? So we've got, let's see, we've got negative 40 minus or plus 100 minus 90 minus 50 plus Fy equals 0. So Fy looks like will be positive. And let's see here. 10 minus 40 is negative 30, negative 80. So Fy is 80 kips. Okay, and that's going to be upwards. The nice thing about doing these shear moment diagrams, you can tell if you make an error when it comes down to it. But so all right. So let's do a little. Let's do the moments now, because we still got to get that moment. Some of the moments in the z, and we're going to do that at the end point, which I didn't really name. Let's just call this point a. Round a equals 0. Okay, so now we've got that 40 kips. Okay, and it looks like it's going to be positive, so we'll make that a positive for its moment, and it's 7 feet down. Okay, then we've got that 100 kips, which is going the opposite direction. And this is 6 feet down. Okay, and then, well, the 50 and the 90, because they're acting in the same location, we can combine them if we want. And I'm going to go ahead and do that. So I'm going to make that a 140. And that's going to be positive, plus 140 kips times 1.5 feet. And then we're going to add mz. And that equals 0. Okay, so let's go ahead and solve that. Let's see here. 40 times 7 is 280 minus 600. That's negative 320. Plus, what's that? 210. So it's negative 110. So mz is 110. Is that right? Okay, I'll go ahead and use the calculator on that just to be sure. 40 times 7 minus 600 plus 140 times 125, negative 110. Okay, 110. Okay, so that's 110 in this direction. Okay, so we can go in here, we can erase these things. I'll go ahead and put, I'll keep them in red because they're, reactions. Not that they're any different or anything. Oh, this is foot kip. Actually, I have no idea if that's a okay way to write this, but I'm going to write it that way. Okay, and this one's going to be 80 kip. Okay, and then we're going to erase these over here because when drawing our shear and moment diagrams, we can't treat them like it's a single force because now we're looking at what happens in the internals of the system. So we have to treat it like, something, more. Okay, so we're going to do, again, rulers help this out tremendously. So we'll go like this. And really, graph paper is the best. So on your exam, I'll have graph paper and you need to use graph paper. I'm not going to be very happy if I have to grade this without graph paper. Okay, because basically this comes out really sloppy if you don't use graph paper. Actually, I say that, but there are some of you who are very capable of doing very neat work without it, but I have to kind of create one standard for everybody. Okay, so this is the shear. And again, we're just going to follow what it tells us to do on the diagram above. If we wanted to, we could start from the left, from the right. I never start from the right though. I just think that that's silliness. Oh, look at this. 5 people. Hey, Rye.
Good morning. Good morning. How you doing?
Good morning. Good to see you. So we're going to go down 20 kips for every foot to the right. Okay, the grand total of that's going to give me down 40. We already kind of figured that out over here. All right, so let's go ahead and we're going to go down. Like the grand total of that's going to get me down to here, which is going to be negative 40 kips. Okay, and I'm just going to go down by that 20 kips for every foot to the right. There you go. Okay, now again, I'm just going to do what this thing tells me to do. So now it tells me to go up by 100, so I'm going to go up by 100. And it's going to put me at 60 kips. Okay, now between that 100 and the beginning of the other distributed force, it's not telling me to do anything. So I'm not going to do anything. I'm just going to stay where I am. Like that. Okay, at which point, I'm going to start going down by 30 kips per foot. Okay, I'm going to do that for a foot and a half. Okay, so 30 times a foot and a half, that's going to be, we're going to go down 45. So at this point right here, which I guess I forgot to put a line, because there is a force right here, right? So what I'm going to do is I'm going to go down by that 30 kips per foot for a foot and a half. And that's going to get me down to about 15. So maybe 15 is about right here. So I'm going to go down until I hit that number right there. Okay, so that's 15 kips. At which point this additional 50K comes into play. And so now I'm going to go down 50 until I'm at negative 35 kips. Okay, so now I'm going to go down 30 kips per foot for another 1.5. Okay, so that's another 45 we're going to go down. So we're going to go down like this. And so that's going to put me at, so I was at negative 35, I went down another 45, so that's going to put me at negative 80. Oh, kips, not kilonewtons. Okay, and then I'm going to use this final 80 right here, and I'm going to slide all the way back up to 0. Okay, notice that technically this line right here should be steeper than this line. If you're worried about your drawing, you could say that you could just write like steep, shallow. Usually in the ones that the book creates, there's usually only one distributed force, so it's not really worth getting all bent out of shape about. So that's just that. Okay, so I'm going to go ahead and erase all this work on the reactions because I think we're good there. Okay, because we might need some work for these moments. Any questions on that shear? I positively loved doing these when I was in statics class. This was like, I don't know, to me this was very fun. So I hope that everybody finds like something in statics where they're like, this really speaks to me. I found trusses really fun. I found this really fun. I hated moments of inertia. And I hated centroids. I didn't really hate centroids that much, but moments of inertia, like you do all this work and get an answer like 32,518 inches to the fourth. And you're like, okay, I don't know if that's a good answer. And still to this day, I don't know. I got inches to the fourth, that's good. I got a length to the fourth, that's about as well as I can do. Okay, so now we've got this ugly thing going on here. And so let's try to make some sense of this for the moment diagram. Let's see, got my little trusty dusty ruler. It's funny because I got a ruler, I'm drawing a perfectly straight line, but Zoom kind of pixelates it. Well, in that case, the ruler slipped, but it pixelates it and kind of changes it. Okay, so anyway, so we're gonna start here. And let's see, so I think about the little boxes that I'm adding here. Like each little box that I'm adding. Okay. I could actually think of the area of each little box I'm adding if I wanted to. But let's just go ahead and think about these boxes. And the first box is a very small box. So it's going to be like that maybe. And the next one's going to be a little bit bigger. So I'm going to add a little bit more. In this case, I guess supposed to subtract a little bit more. And then each box is progressively bigger. So this is going to be a curved line. Okay, now I'm going to draw it. I'm going to freestyle it for the whole, distance here. And we're just going to go like that. Okay. And the nice thing here is we can do the area of that triangle to figure out where we're going to end up. And so I'm going to do 1/2 the base times the height. So the height is 40 or negative 40 times the base, which is 2. Okay. And then 1/2 of that divided by 2. So we're going to get negative 40. So this value right here is negative 40 foot kips. Okay, and we'll find the equation for that line shortly. Okay, at this point, I'm over here and now I'm going to start adding some positive amount. And that positive amount will be the same with each step to the right. Okay, so it's going to be a straight line going up. And I can figure out where I'm going to end up by just doing, well, 60 times 3 is 180. So I know I'm going to go up by 180. Okay, so base times height, what is the area of that rectangle? Okay, so 180, I'm going to add that to the 40, and I'm going to end up at 140, which is a pretty big number. So I'm going to try to draw this pretty big, but I don't want to go as big as where 140 should be because I don't have that much space. Okay, so we were at negative 40, and I went up to 140 foot kips, okay, because I added that 180, which was the area of that rectangle. Okay, so now we've got a weird thing going on here. This first box right here is essentially the same as the last box in the one before. So the slope is the same. Like if we notice this box right here and we compare it to this box, they're basically the same. Maybe it's a little bit less. Okay, and you'll notice that as we go this way, the boxes are getting smaller. Okay, notice that right here, I still have a positive slope because I'm still going up. All right, so now what's that value? Well, we have to figure out the area of this. Is that a trapezoid? What kind of shape is that? Trapezoid or rhombus or I don't know. Anyway, it doesn't matter. When you want to find the area of one of these things, you take the average value here, between 15 and 60. So it's 15 right here and it's 60 right here. So the average of that, and you multiply it times the base. Okay, so that's going to be 75. Okay, 60 plus 15 is 75. We'll divide by 2. That'll give us the average height. And then we multiply times the base. And the base in this case is 1.5. Okay, so 56.25. So that's the area of this traporhomboid thing. It's 56.25, and it's a positive. So we're going to add that on to the 140, and I'm going to get 56.25. So it becomes 196.25 foot kips. Okay, so then immediately the slope changes and it goes negative. So it's going to be a discontinuity here. But what I want to do is, so basically this thing is going to do this, right? It's going to because it's going, this is the steepest bit right here. This is the least steep bit right here. Okay, and I'm gonna have to figure out where I wanna draw it going to. So I need to figure out the area of this particular traporhomboid thing. I'm just gonna call them trapezoids. Okay, so we'll do 35 and 80. 35 plus 80, plus 80, okay, is 115. Okay, divide that by 2, so that's the average height of that thing, is 57.5, and I'll multiply that times 1.5, which is its base, and I got 86.25. Okay, so that 86.25, if I subtract that out of the 196, I end up at a point maybe here, which is going to be 110 foot kips. Okay, notice there's a discontinuity right here. Okay, and then you'll notice the last bit we have is this 110. Okay, and that's what kind of balances this all out. And you'll notice that it seems a little weird that we're going down for this 110 when this is a positive 110. But really what's happening is you could actually think of it as if you were starting on the right, if you were starting here and you went that way, you would start by going up. Okay, for that positive 110. So that's really the way you kind of have to think about that. It's a little convoluted logic, but it is the way it is. So yeah, so then this looks like that. Oh, come on. Can we get that line back? Okay, so that's the whole thing. And again, by getting this 110 here and getting this negative 80 here, which match our numbers here, we can feel pretty good that we've done this correctly. Again, usually we shade these in when we're done. Okay, now I was going to show you, and I kind of messed up a little bit because I was making up this problem and I got overly excited. And I put in this extra 50 kip force. But I kind of wanted to explain, so like, you know, the typical question here is the shear max equals what? And in this case, it looks like the shear max is 80 kips, okay, which is all the way at the far right. So if this thing were to break, basically it would break right here, right next to A, due to shear. And if it was to break due to a moment, okay, it would break at, you know, right here, you know, at, you know, whatever that value is, because the max moment there is 196.25 foot kips. Okay, so the last thing that I kind of wanted to drive at here, and this is the last bit that people don't like, is, and I kind of did this wrong. So what I'm going to do is I'm going to make an incorrect. So I'm going to assume that this 50 was no longer here. Okay, let's just imagine a world where that 50 is no longer there. It would change. Nothing's going to work out on this side. Okay. So nothing's going to work out on that side. So let's just ignore the fact that nothing's going to work out. Okay. But what I want to do is I want to imagine a world, and probably you can figure out pretty easy how this would change. Let's go ahead and figure out how this would change. This is still going down like that. Boom. Like such. Okay. And so I can still probably figure all this out by doing, okay, well, I started it right here. I was at, I was at 60 kips. And then I'm going down at 30 kips per foot. So after I've gone 2 feet over, I'm going to hit 0. And then if I've gone another third, I'm going to get it to negative 30 kips right here. Right? Okay, if I go down 30 kips per foot, so then this number right here is actually going to be 30 kips. Okay. You could technically use these to solve these problems if you wanted to. I don't necessarily recommend it. Okay. So what we can do here, is what would happen is, okay, basically I'm adding positive area. I'm going to do this in green. All of this is positive area. So that my slope is positive as long as I'm in this green area. Once I cross into the yellow area, I'm going to have a negative slope. So what's going to happen here is this thing is going to keep going up until it peaks right here. Okay, that's where the slope is 0 because I'm no longer going up and now I'm going to come back down. Okay, and then this is going to and then I'm going to start to come back down. Because the question is, a lot of times in this case, so I might say, well, what is our moment max and what is our shear max? Well, shear max, we can just look at this diagram over here and well, it's 60. Come on, 60 kips. But our moment max, well, we know where it's happening. It's happening right here because that's where it stops going up. And we know that this number is going to be bigger than the 140 and it's bigger than the 40. But we don't know what that value is. So what we need is we need to figure out the equation of that line. Okay, and so the way we're going to do that is, well, probably the easiest way to me is we figure out the equation of this line right here. And then we integrate that. I mean, we take the derivative. Well, we integrate that. Well, here, let's just do it. Okay, so I want V as a function of X. This is going to be from X equals 5 to 8 feet. Okay, well, that's really not a very mathematical way to write that, is it? 5 feet is less than X is less than 8 feet. Okay, V of X. Well, we know the slope of that line. It's negative 30 foot kips. Sorry, kips per foot, excuse me. 30 kips per foot. Okay, times X. That's the slope of that line. Okay. And then we need to figure out its y-intercept. Okay. So we're going to go in there and we'll say, okay, well, I know that the shear at 5 feet is 60K. Okay, so what's my y-intercept? Well, my y-intercept in this case is, what's that? Negative 150, bring it over to the other side, 210. Okay, so we erase this number right here. I'm gonna go ahead and say 210 kips. Okay. All right, cool. So we're like, all right, now we're cooking with gas. Y'all see how I did that? That makes sense? You guys look so bored this morning. Stephanie, did that make sense? I saw you unmute for a second.
Yeah, I did.
Okay, all right. So Stephanie's cat doesn't look as bored, but.
Not bored, I'm just tired.
Yeah, well, I can only see your cat, but, oh, Parker, sorry, yeah. Tired is okay, I'm tired too. Mostly I'm hungry. My feelings are not hurt. I was one of those, some people have those eyes that kind of like droop and sometimes they start drooping in turns. I was that guy, And then when I went to grad school, I remember there was a guy who'd come to class every day and he would just bring a pillow and he would just put it on his desk and he would go right to sleep. And I was always like,
Okay, well, that's just rude.
well, it is rude, but also I was kind of like, you don't have to be here. There's no, attendance is not required. Just stay home and get some sleep. I guess he thought he was gonna, Anyway, so then we need to get the moment equation. What we're gonna do is we're gonna integrate that equation. And so we're gonna get equals negative 30 kip per pound. Okay, X becomes X squared on 2. There's that curve that we were looking at, plus 210 kips times X, okay, plus some initial moment, which I don't know, I'll call it M1 because it's the first one I've done here. Okay. Now, again, we have to, now this one's a little bit unfortunate because we have to pick a spot where we know the moment. So the easiest spot is right here, this 140, right? We can't pick that 110 because that 110 is no longer correct. We're gonna pick that 140. And so what's that? That's at X equals 5. So M of X equals, I'm gonna get rid of all the units here just because I have kind of a space limited thing here, 5 squared on 2. Oh wait, sorry, that MX is 140 plus 210 times 5 plus whatever this M1 is. Okay, so I'm gonna go ahead and plug all that into my trusty dusty calculator. Negative 30 times 12.5 plus 210 times 5, that's 1050, equals that number, 675. Should go ahead and subtract from 140. And we'll get 535. So M1 is negative 535 foot kips. 535 foot kips. All right, now, question. How would we figure out what the max is? There's actually, I can think of a few very nice ways we can do this. No ideas? Calculus, remember calculus 1, I think. All right, so there's a few things we can do. One, I can note that the slope of this line is 30 kips per foot. I started at 60 feet. Excuse me, I started at 60 kips, so I went down 30 per foot. So in other words, this distance right here is 2 feet before I hit, no, sorry, that's all the way to here. Before I hit the 0 line. Okay, that's the point where this thing started to go back down. So I can just plug in x equals 2 for this, not 2, x equals 7. So if I plug in x equals 7, that'll give me the point 2, 5, 7 to where I now have a negative slope. So everything to the right of 7 has a negative slope, and so therefore it has to go back down. Does that make sense? Okay, so basically I could plug in x equals 7 right there. And so what we would do is we would just plug that in. And if I do that, I'm going to get m of x. M of x equals, let's plug that 7 in, negative 30 times 49 divided by 2 plus 210 times 7 minus 535 equals 200. 200 foot kips. Okay, so 200 foot kips. Okay, that's how we do it. Okay, if I wanted to know the value here at the end, okay, I would just plug in x equals 8. Okay, so this is, this is m at 7. Okay, m at 8. Okay, and we'll note that m at 8 should be less than m at 7. And there's two ways to get that. I can either calculate the area of this triangle and subtract it off of the 200, okay, which is pretty easy, right? So that's 30 times 1, that's the base, and divide by 2, so it's going to be 15. So I'm going to be 15 lower than that 200. So I should be at 185, or I can just plug it into that formula. I can plug the 8 in, and I can go 8 squared divided by 2, 32, times negative 30, plus 210 times 8, minus 535 equals 185. So that was expected. Okay, 185 foot kips. So this is 185 foot kips. Okay, the M max is 200 foot kips though. Okay, if you just had this moment equation right here, and you didn't have this shear equation, or let's imagine you didn't know where this thing happened. If you're like, I don't know where this happens. I don't know where, I just want to know where the max is. Do you remember how to get the max of a parabola? So this is a parabola. Do you remember how to get the max of a parabola from calculus? Okay, well, what we do here, okay, is whenever you want the max of anything, and this is probably one of the main purposes of calculus, but of course they spend too much time trying to teach you how to find what a derivative is and what an integral is, and not enough time like teaching you how to use them, which is a colossal error in my opinion. what we do is we're going to take the derivative of this moment equation with respect to x. Okay, so that's telling us the slope of this line. Okay, so derivative in this case would be, well, let's see here. We're going to bring the 2 down, and we're going to get negative 30 kips per times x plus, do the derivative of the next term, 210 kips. Okay, there's no plus c or anything, right? So this is the slope of this parabola. And if we want the max, we want the point where that slope is 0. So set that equal to 0. And then we solve for x. Notice this is the exact same equation I just blocked out, by the way. Okay, but if we solve for x here, then we get x equals 210 divided by 30, which is going to give me 7 feet. That tells me where this thing maxes, or it could be a min, but it tells me where the slope is 0. Once you know where the slope is 0, you plug it in up here. And that will give you the moment at that location. Okay, hopefully that makes sense. You know, this is one of the reasons why I'm very critical of the fact that we teach a lot of calculus and then we don't use it. And I think that when you learn this in a calculus class, you're like, whatever, you know, you just like, what do I got to know for the test, you know? But then all of a sudden when it gets re-exposed, sometimes it's like, oh, that makes sense. That's not so bad, you know? So anyway, hopefully this is making sense. We've got like 8 minutes.
I have a question.
Sure.
Talking about shear max, is that always going to be a positive value, or are we talking about like absolute values?
It's absolute value, and that's why they put these absolute things here, to let you know.
Oh, that makes sense.
Because we don't care if, like in this case, yeah, so in this case, like right here, this is a negative shear right here, for example. Oh, come here, give me this, right. Okay, that's a negative shear right there. And this is a positive shear right here. Okay, and so what this means to me is that this side wants to go up like this, and this side wants to go down. I always think about earthquakes along shear faults. Okay, and what difference does it really make if that's your shear versus like somewhere else where maybe, you know, down here we've got this is going on. And so let's see, oh, I guess that's the same. So we've got this going up and this wants to go down. Is that right? I struggle with the signs on shears. Yeah, so regardless, like, it doesn't matter. Usually what they want to know is, can this thing hold a shear like that? It doesn't matter the positive or the negative. There will be cases for moments where you're definitely going to want to split moments into positive and negative. And the reason for that is because, like in this case over here, I mean, it won't matter in this class, but over here, this is all a positive. So this is a smiley portion of the beam, and this is a frowny portion of the beam. And so the way that matters, so if I draw it in green, is, let's see here. So here's the point where this thing goes from smile to frown. So frowny over here means this beam is going to kind of have to take this shape. And then the smiley bit is going to take this, you know, is going to smile. Right. I mean, obviously bad drawing. It's not going to be so discontinuous right here. But anyway, you will care about this because what will happen as you get into like structures is you're going to care whether or not something is, which side is in compression and which side is in tension. So in this case, the inside, these sides are compressing and these sides are tensing. And so on the tension side, what you do is you put a lot of rebar. So like if this is concrete, you'll put reinforcing bars of steel inside there, because steel is really good in tension, but concrete is very good in compression. And so what you want is you put rebar into the side that's going to have a lot of compression. You actually put rebar on both sides, but you put a lot of rebar in the side that's going to mostly be under tension. So you will care about the smiling and the frowning So there will come a point where you will care about positive versus negative moments. I don't recall there ever being a point where you care about positive versus negative shear. I know that's a long-winded answer, but for the most part, in class, we only care about the absolute value, I guess. So,
Would I ever use the second derivative to figure that out?
so
Concavity or?
yeah, if you did the second derivative, you would figure out the concavity of, well, you'd figure out the concavity of this line, but basically anywhere where the shear is, anywhere where the moment is positive. So all of this is a smile. So if your total moment is above that line, above zero, so basically you would just look at this equation, and if the value is above zero, you don't have to take the second moment.
Okay.
Take the second derivative. Does that make sense?
Yes.
Okay. Right. So right, but that's the right idea. If you took the second moment, the second derivative, you would just be getting the concavity of this line. But what we really care about is the value of the moment. If the value of the internal moment is positive, then it's going to be getting, twisted like this, in such a way that makes it smile, and if it's got a negative value, then it's, going to be, it's going to be frowning. So at least that's just the way I think about it anyway. I'm sure everybody has their own ways of doing it. Also, one thing you could do here, if you wanted to, I know when I did these, I'm not going to do this to you guys, but I was definitely forced to find, and maybe this was something we had to do in structures class and not in statics. Your book doesn't seem to do this, so I'm not going to go into it this way, but is to maybe find that point right there. The point where you end up at, zero moment. And what you would do if you wanted to get that, I'll show you. It's not terribly complicated, because basically what you would do is you would say, well, we need the equation for that line. And so we would change these out. I guess this is as good a use of the last 2 minutes as any. Come on, just delete, you punks. Deleting this thing is a real, okay, whatever, close enough.
So there's only one point there where the moment is zero.
Right.
1 point on the bar.
Right. And so really at that point, this thing is momentarily straight. Okay, like it's neither frowning nor smiling. So it might be like, this, and then it starts to do that. I don't know. I can't draw it. But yeah, so that would be between between 2 and 5 feet. And we would just need the equation for the moment there. And so we would start with, well, what's the equation here? Well, V of X for that entire section is just 60 kips. All right, that's pretty straightforward. It's not even a function of X. So let's go ahead and do the moment of X. And it's kind of nice, like the more of these you do, the more you're like, oh, I see, we're just doing the same thing over and over again. The moment of X, we're going to integrate that, 60 kips times X plus, some constant. Okay, and maybe I've already used M1, so let's call it M2, And then we would say, well, let's use a point we know. We can either use this 140 or I'm going to use this negative 40. So negative 40 foot kips equals 60 kips times what is that X value? That X value is 2 plus M2. So M2 is, what's that, 120. It's going to be negative 160 foot kips. So we'll go here. And we'll make that negative 160 foot kips. And if I wanted to know where this thing goes from being positive to negative, I would say, okay, notice a few things there here too before I do that. Notice that this tells me that this is a straight line. This is not a parabola. So from here to here, this is a straight line. As we already knew, right, by the argument I made over here of just like adding little boxes, and each little box is exactly the same. But anyway, we could say, okay, well, where does this equal zero? When is the moment zero? The moment is zero at, at X equals, minus 160 foot kips. So at X equals 160 divided by 60. So on 160 divided by 60 equals 2 2/3. Okay, so that's, so that's 2/3 from here is where that thing equals 0. So if somebody ever were to ask you that, that's how you would get at that, And in fact, these can even be easier if sometimes you can just define an X for each section. So you can have an X right here, an X right here, and an X right here. That's how I used to solve these because I didn't want to deal with, that just makes it a little bit easier, but it just makes your y-intercepts smaller numbers. But, you have a calculator, so the size of the numbers shouldn't matter. Anyway, that's all I got. Any other questions? Okay, so, since you guys are here, if you guys felt like sending me an email about what you'd like to do with the last one of these on Thursday, that'd be great. I mean, on Wednesday, that'd be great. Or maybe I can just, I don't know, maybe I'll just work I posted last semester's exam. So maybe I'll just work some of that. That might be good. Might be good to work on it before then. So yeah.
That would be helpful to see like kind of similar problems
Sure.
that we'd expect to test.
So what I would recommend then is if you guys would just try a few of them before you get on so that you have questions and instead of just watching me work them and going like, oh yeah, that makes sense. Know what confused you. It's always more helpful than just watching. But of course you can just watch. So whatever you want to do. So yeah. So anyway, have a good day. And I'll see you guys Wednesday.
Thank you.
All right, guys. See you.
Yep, have a good day.
See you, Austin. See you, Hannah. Stephanie. Let's see here. Hi, Stephanie. Let's see. And recording. Stop.